Okay, let's get started. Welcome to the last lecture of the course. Today we will continue our discussion from the last lecture. We will talk about, last lecture we talked about Lagrangian relaxation technique, its augmented form, and we talked about the fundamentals of ADMM. Today we will continue our discussion. Specifically, we will talk about ADMM and its different variants, and also we will have a focus on its potential applications to power and energy systems. Good. So hopefully after this session, you will be able to have, you will have a clearer idea about the applications of Lagrangian relaxation in general and augmented Lagrangian relaxation and ADMM as a specific way to solve augmented Lagrangian relaxation their applications to power systems, energy and power and energy systems. Hopefully also after this session, you will have a clear idea about two different variants of ADMM, which are very helpful. You can use it in power systems extensively, namely exchange ADMM and consensus ADMM. And hopefully after this session, you will be able to implement these techniques to stylized illustrative examples. Let's see. So today our main reference is this paper by Stephen Boyd et al., which is about ADM. Well, some recap from a previous lecture about ADMM. Here I use term conventional ADMM just to, to have a contrast, to compare it later against different variants of ADMM. So I'm talking about the ADMM that we talked about it last lecture. So if we consider this following, optimization problem with two variables, X and Z, while we have objective function, separatable objective function, the first term just related to X, the second term in the objective function just depends on Z, then we have two different constraints. The first one just X dependent, the second constraint just Z dependent, while we have a complicating constraint or linking constraint that links variable X and variable Z. And definitely, we already learned that the last constraint is our complicating constraint. It means that if we relax it, then the original problem will be decomposed to two different subproblems, one for X and another for Z. So we'll have two subproblems, X update subproblem and Z update subproblem. But so what we did last time, we wrote the equivalent max-min problem. So we bring the complicating constraint to the objective function, as we did here. So now it's, this term is our partial Lagrangian function. Then lambda is our dual variable. So we need to write a max-min problem to be able to achieve the optimal value of lambda. Then also yesterday we talked that in case f of x and g of z, they are linear. It means that their first derivative is not continuous. They are not continuously differentiable. Then the gradient-based methods like ADD, they will not work out. So we need an additional penalty term in form of, in quadratic form. And we added this term. It changes to problem, but the optimal solution will be unchanged because in the optimal point, we know that the value of this term will be equal to 0. It comes from our original equality problem, equality constraint. So we added this penalty term as a regularizer or as a penalty term, what it did. So it makes our original objective function continuously differentiable. Then we said that, well, this problem is equivalent to our original problem at the optimal point, but it's not decomposable. First, because of this maximization operator. So what we did, we fixed lambda to lambda bar. So we fixed lambda to lambda bar, so we got rid of the other maximization problem. So now we have this problem. If we didn't have the last term, the problem was decomposable in x and z. But this term doesn't allow the problem to be decomposed because it's a square term and we will have x times z, a bilinear term there. So though the penalty term, it makes the objective function continuously differentiable, but the cost is that our problem is not decomposable anymore. So what we did, we used the solution is Admm, the way that we can make the problem again decomposable. There are also other alternatives, like a technique that I called APP, auxiliary. I forgot. Yeah, APP. Uh, yeah, auxiliary problem. Yeah, right now I forgot what this abbreviation stands for. But what ADMM is, we saw that it's very easy. We alternatingly solve X and Z. What it means, so we have two subproblems, X update and Z update subproblems. For the X update problems, we determine the optimal value for X in the current iteration new. Let me change the color. So new is the current iteration. So we find the optimal value of x in the current iteration, just the optimal value, the objective function of the original problem related to x. The one for z is a constant. And then we have lambda, which is our lambda bar, which is our fixed dual variable, times the term of the complicating constraint related to x. And then we have our penalty term. And note that here f was constant from the beginning, and also z comes from the previous iteration. It is constant. And this is our original constraint related to x. Similarly, we do the same for z. So we have z update subproblem. So the original objective function fixing, the fixed dual variable coming from the previous iteration, the term of the z dependent term from the complicating constraint, and our penalty term. Again, similarly, z in iteration new is our variable, while x now comes from the previous subproblem, but in the same iteration is a parameter constraint to our original constraint. So yesterday we talked that we can use the updated x in z subproblem, but the cost is that now we have to first solve x update and then z update. So it means that in each iteration, we need to solve our subproblems sequentially. It will converge faster because we are using the most updated information about x in the z update subproblem, but we are losing the capability of solving the two subproblems in parallel. The other alternative is that instead of having x in iteration new, we use the value of x that we got in the previous iteration, new minus 1, then we can solve x and z subproblems separately in parallel. Also, we talked about the way that we can update lambda bar over iterations. It's simply the value of lambda bar in the previous iterations plus gamma, which is our, let's say, coefficient or penalty factor, which also appeared in the objective functions, times the residual value for our equality constraint. Yeah, that's what we had last lecture about conventional ADM. Is it clear? Do we have any questions so far? Yes. So let's start. Jan asked that, can ADMM only be applied to problems consisting of a summation of just two functions, or is it just it's just an example? Of course, it's just an example. We had just two variables and let's say two block or two part objective function, but it could be anything. As long as by relaxing a complicating constraint, your original problem is decomposable, then we can use Adm. So this is just an stylized example. Good. So there is something called scaled Adm. It's not a different technique. It's exactly the same representation of our Adm, but in a bit different way, but it's equivalent to our Adm. Let's see what it means. So in our ADMM in the last slides, we had two terms in the objective function, one as lambda bar times our, let's say, the term coming from the complicating constraint plus our penalty term, right? So we can do some math and we can combine them. So nothing is changing. So we can present our ADMM in a different form that we call it scaled ADMM. And as you see, now in the objective function of X update, we have only one term, one quadratic term, but it's a bit extended. So we don't have the linear term anymore in the objective function, which was lambda bar times a term. We don't have it anymore. And also instead of lambda bar, we have something new. We call it scale dual variable. And here u bar is just 1 over omega, sorry, 1 over gamma, which was our penalty term, penalty coefficient times the lambda bar. And this is the same way we can, in a similar way, we can update U bar. And similarly, we can do for Z update. So as an exercise later, you can check why this scaled ADMM is equivalent mathematically to our original ADMM. It's easy. You will see. You will find out in a very straightforward way. So if in papers, in books, you see ADMM in this form with only one term, quadratic term in objective function, it's the same. It's our ADMM just in the scaled form. So Achilles asked, gamma on the penalty term is the same as the step size? Yes. Yes. So in our ADMM, this gamma and this gamma in the objective functions, they are identical. So is the scaled ADMM clear? Rafa said, I didn't get the advantage on using the scaled ADMM rather than the conventional one. There is no mathematical advantage. Just notationally, it's easier. It's more compact. So there is no computational advantage. It's just notational advantage. So I put it here just to tell you that if you see ADMM in the papers like this, it's our ADMM just in a reformulated way. It's equivalent. Clear? Good. Let's have an example. Economic dispatch problem, which is the same as optimal power flow problem, but without network. It means that we have only one, we have a single node. Let's go for a simple case study with 3 generators, deterministic problem, no wind farm, nothing. And let's assume that these 3 conventional generators, they have quadratic cost function. So G from 1 to 3, so this is our, this is their production cost in a quadratic form. It's not market clearing problem because in the market clearing problem, the generators, they bid in a linear way or in a piecewise linear way. Here it's economic dispatch. Let's say that we have just a single system operator and we have 3 generators. They have quadratic cost and we are trying to minimize the system cost. The demand is inelastic, so we are minimizing the cost, not maximizing social welfare. And simply, we have a generation limit for 3 generators and power demand balance equality. And lambda is its dual variable. Yes, so this is the definitions of different parameters and variables. It's a simple. So remember that our objective function is quadratic, our original objective function. So, and also you know that the last constraint is complicating constraint. We can remove it, we can relax it, and then we can use Lagrangian relaxation. And since it's quadratic, we don't need to add any additional quadratic penalty term. So we can use directly Lagrangian relaxation technique, or also called dual decomposition. So easy equivalently, we can bring the complicating constraint to the objective function. Lambda still is variable, but it's a variable of the other maximization problem, not variable in the inner problem. So this is a exactly equivalent problem. But then to be able to decompose, we got rid of max, we fixed lambda to lambda bar, and this is our let's say relaxed problem. Then we can decompose this problem one per generator. How? It means that each generator just minimizes the cost. Yes, also we have here CG, but it's a fixed cost in the objective function. We can remove it. So this is the total production cost of the generator minus lambda bar PG, right? Subject to the local generation limit. So we have three subproblems like this, one per generator. And remember lambda bar, or lambda, it's a dual variable of our power balance equality. So lambda, if we were talk about the market, if we talk in a market context, it's the price, right? So with this, in each subproblem per generator, so what is the objective function of each generator if we think in a market way? We are maximizing profit, right? This is the production cost of the generator. This is the revenue. So we are minimizing cost minus revenue. So we are minimizing minus profit, or we are maximizing profit. Is it clear so far? Good. So yesterday we learned if we use LR, how to update dual variables, lambda bar over iterations. The simplest way is to use subgradient methods. We have more elegant methods. For that, you can simply check this book. So that's the nice maybe illustration way. So what happens? Now we have three subproblems, one per generator. Each of them, they are maximizing their own profit, subject to their own constraint, and that's it. Does this remember you something we learned from lecture 2? Equilibrium problem. Exactly. This is equilibrium problem. That's one of the ways we can solve equilibrium problem. Instead of solving using MCP, deriving KKTs, putting all together, we can solve equilibrium problem for the market in a distributed fashion, right? So each generator in the corresponding subproblem maximize her profit. Here we have, in this case, coordinator, or if you like, call it market operator or whatever, just lambda bar update. I mean, the coordinator updates prices. So now the system operator or market operator is not determining the production of generators, just updates the prices, and the generators, they are doing self-scheduling. For given prices, they maximize their profit, and this way they determine their optimal quantity to be produced. So in each iteration, the three generators, they submit their quantities for given lambda bar, and then the coordinator updates the price and sends back the updated prices in the new iteration. And it should work. And if you solve the market problem in this way, it works out, no problem. The cost is that it's an iterative solution, But the beauty is that you don't need to derive KKT, you don't need to solve MCP problem. So in the market context, this iterative approach is referred, we refer to it as Valrassian action. It comes from economist Walras. So Valrassian action is an iterative way to clear a market. And the concept is simple. The coordinator disseminates prices. Then the generators, or let's say market participants, they respond to the price. Then based on the response of all market participants, the system operator or auctioneer, let's say the auctioneer, updates the prices and then sends back the updated prices to participants. So this is what we call it as Walrassian action. And Lagrangian relaxation is a way to implement Walrassian action. Is it clear so far, everything? Good. So a discussion. Our previous example with 3 generators, it was very super easy. If we add elastic demand, what should we do? What happens? Now we have the fourth market participant, which is elastic demand, who maximize her utility. Carol says more subproblems. Exactly. So now here, D will not be a parameter anymore. It will be a variable. So we need to add the fourth subproblem for elastic demand, who tries to minimize minus utility, right? Subject to her own demand constraint. So the demand sends, let's say, demand of her demand in iteration new, and then the auctioneer sends back also the updated price in the next iteration, right? And here, no, it's exactly the same. Just here, D is not parameter anymore. Auctioneer receives D, so D becomes D in iteration new. That's the only difference. Is it clear? Clear? Well, to have this system working, what should this problem, I mean, can we have it linear or not? It should be quadratic. QP. Yes, exactly. Like all subproblems, the subproblem for the fourth generator also needs to be quadratic. Good. Now the next tricky question. Now we have network, transmission network. We like to add it to Walrassian action. What should we do? How can we add transmission network to this action, to this Valrassian action setup? Remember equilibrium problem from lecture 2? Yes, Raja says another player. Nuran says add as a subproblem. Exactly. So also transmission system owner, based on what we learned from lecture 2, is another subproblem. Yes, so transmission system, let's say owner, not operator, transmission system owner. So for the transmission system owner, what is the objective function? Maximize what? Do you remember from lecture 2? If we have a network and we write the market problem as, yes, congestion rent, exactly. We need to maximize congestion rent subject to, let's say, the network limits. The network limits, exactly. So we need to add this subproblem to our picture. Good, very nice. Any mathematical challenge? If we add a transmission system owner, do we have any mathematical challenge? Yes, Carol. As Carol said, the congestion rent is linear function. So my students in the last version of course, I asked them to try to solve market problem with transmission system using this Valrassian action. They couldn't get convergence. And I guess if you try the same, it will happen. So we have a mathematical challenge there. If we add a transmission system, we will have problem there. Let me check the questions, the chat box. Nima says, what are the benefits of Valrassian action? Well, I'll talk about the benefits a bit, but the first benefit is that, it's a different way to solve an equilibrium. If you think of equilibrium, you need to solve MCP, while here you don't. Remember, in perfect competition, we were lucky, and our equilibrium reduced an optimization problem. So optimization problem is the easiest way to solve a market clearing problem. But as long as you add any externality, then our equilibrium problem may not have any more an equivalent optimization problem. Then you have two options: either solve equilibrium problem using MCP, mixed complementarity program, or you can go for this distributed solution. And sometimes you may see that the distributed solution technique is easier to solve, perhaps. It depends on how many, subproblems you have, how big is your problem. That's one benefit. Second, we will talk about privacy in very soon in some slides. Chandra said, but then prices should be nodal. Yes, the prices should be nodal, exactly. When we add the transmission system to this picture, instead of lambda bar, we have to have lambda bar n. So the market operator or coordinator will disseminate nodal prices, not uniform prices. Yeah, that's totally correct. Yannick said, shouldn't there be multiple lambdas? Yes, definitely. Yes. Yeah, any other questions so far?
So Jalal, you said that last year your students struggled to solve this problem. I assume those were numerical issues, right?
No, because as long as you add transmission system with linear objective function, it doesn't converge. But as long as you eliminate a transmission system, then all the remaining participants' problems, they have quadratic objective function, then it converges.
Sure, but I mean, you could make the transmission system problem quadratic. I mean, that you can just introduce a quadratic part, but if you introduce a small quadratic component, then it could be numerically difficult to solve, I guess.
Yes, that's true. What you can do, if you have a linear objective function, thanks for telling that. Let's say f of x subject to whatever. Assume that f of x is linear. So what Sebastian is suggesting is that we can add something like, let's say, beta, and beta, let's say it's a very small, it's 10 to the minus 3 or something like that, x squared, right? Something like that. So now we are not changing the objective function much because beta is very small, but with this regularizer, we are making our objective function quadratic. So to be honest, I don't remember if my students in last versions of the course, if they applied or not. Yeah, I don't remember, to be honest, but maybe, yeah, you can try it and tell me with this regularizer, can you get convergence or not? Sebastian, did I answer your question?
Yeah, I mean, I know the technique. I'm assuming I can try it, but I'm assuming that if you do that and the beta is quite small, then you might have numerical problems with your solver, not so much theoretical problems.
Might be.
I'll give it a shot.
Yes, we have to check it out. Brian says, does any market operator use Valrassian action to clear the market? To my best knowledge, in electricity markets, no, but maybe in other markets they do. You don't need to have necessarily electricity market. You can use this Valrassian action for any market, generalized market. In other markets, do they use? I don't know. Let me continue. Another discussion about Valrassian action coming from Lagrangian relaxation is about privacy. There is a belief, common belief, that distributed algorithms, here applied to market clearing, but it could be to any problem, to OPF problem, to any other problem, they preserve privacy, the individual privacies. What does it mean? Here, each generator, they solve their own problem, and they respond to, for example, here to market price. But what it means that, for example, if we assume that Pmax 1, let me change the color. For example, the capacity of generator 1 or the cost function of generator 1. This generator doesn't share those information with others, with generator 2 or 3 or auctioneer. So this is why there is a belief that this algorithm, any distributed optimization algorithm, preserves privacy. And it looks so, right? Here, except for generator 1, no one else knows what her cost function and constraints are. So the question is that, does this distributed setting necessarily preserve the privacy of agents? What do you think? Sebastian says practically maybe. It's a very diplomatic answer, Sebastian. What does it mean?
What I mean by that is that mathematically, you can probably over time learn what somebody's objective function is like, but practically, depending how many agents there are, depending how complicated your problem is, it might not be worth it or might not be numerically likely.
Yes. Exactly.
Also depends how often your constraints change.
Yes. So the first thing that one can think is that the people, they see, at least the auctioneer, and maybe the others, any adversary, they see that how with different prices, the generator responses. So maybe over time, over iteration, we can learn. I don't know if you're familiar with adversarial models, or you can call also attack models. It's any model like reverse engineering that based on outcomes, you can be able to reconstruct the original problem. So let's say that we have optimization problem as a black box. We know that there are some inputs and some outputs. So with inverse engineering or reverse engineering, if we see enough Y over different iterations over different time, then, and also we know X here is price, Y is the quantity of the generators. So maybe by adversarial models, we might be able to understand what this black box is. So for example, you can use inverse optimization, which is exactly doing this, optimization. Or you can use techniques like Bayesian inference, or even you can use some techniques coming from machine learning or deep learning. Maybe you might be able to reconstruct what this optimization problem is, right? And Sebastian correctly said that it depends how practical it is. There might be many number of generators, so it might be hard to detect. But remember, if we have network, instead of lambda, we will have lambda, the nodal prices, lambda n. So the auctioneer, at least, I mean, in each node, we might have not many agents. So maybe for neighboring agent, if we have two agents in the same node, maybe for the neighboring agent, it will be easy to understand what the neighbor agent is doing. Clear? So what I'm saying is that, yes, distributed optimization, it preserves privacy, but to some extent. We are not saying that absolutely it's a privacy preserving mechanisms. Nuran said, or let me check the chat box. Nima asked, but they respond to gamma, so sensitivity of their cost function. What is gamma?
Sorry, I meant lambda, but
Yes.
I think we discussed what.
Okay.
Yep.
Nuran said, can there be an inverse optimization trying to obtain back inputs auctioneer? Yeah, definitely. I mean, mathematically, we have inverse optimization tools, either from Optimization Society or Machine Learning Society. Akila said there is an inverse optimization approach to learn other players' function. Yeah, there are many papers about inverse optimization. If you are interested, I can share with you after the lecture. But anyway, do you have any approach to make it privacy preserving? Can we augment the privacy of distributed optimization? Do you have any suggestion? How can we improve the privacy preserving property of this algorithm? Any initial thought coming to your mind or not? So my first tip is that, yeah, maybe it's not a good idea to write in our papers that our distributed optimization algorithm guarantees privacy preserving. Maybe it's not 100% accurate statement. Jan says peer-to-peer communication, the same. Even in the peer-to-peer communication, you share something and see the response. So whenever you share something, you send the signal and then you respond. For a signal, you respond. As long as you have this setup, the people may learn. So let me move. I'm not going to talk about this concept, but there is a concept called differential privacy. And reference one is kind of the seminal document for differential privacy. I don't know how many of you knows about this concept. I'm not going to teach it here, but I'll tell what it is. What you can do, just in a very simple description, is that the generators, that's the first approach, they can share not their exact response, but with some noise. So let's say that instead of sending P1 in iteration new, maybe we can say P1 plus epsilon, and epsilon is a noise, but not a random noise. It should be designed properly from some properly designed distribution. And this epsilon could be dynamic, not static. It could be dynamic over iterations, right? Or the auctioneer can do and send back lambda bar, not the updated lambda bar, but the noisy price. So with differential privacy, we will learn how to properly, optimally, carefully add this noise, making sure that no adversary will be able to reconstruct the local information of generators. Is it clear? So how to design this epsilon, the noise, it's the critical point. So you can watch this video by my former colleague at DTU. It's about differentially private distributed OPF. It might be interesting to you. Sebastian says, surely this noise needs to be included in the platform design so it doesn't destroy convergence. Very good point. So this epsilon, first of all, by this epsilon, you are compromising the optimal solution. So we will end up in a suboptimal solution. So the question is that how much privacy is important to us? So you have to have a trade-off between privacy cost and suboptimality. That's first things. So you need to have optimality guarantee. But before that, you need to have convergence guarantee. And also before optimality gap and convergence gap, optimality guarantee and convergence guarantee, you need to have feasibility guarantee. So it's a very tricky business, but it's a very interesting, and there's a very beautiful math behind it. So if you are interested to learn about that, just go and search and learn about differential privacy. Good. Yeah, I wouldn't like to talk more about differential privacy here, but I think it's a nice intro for you to know what it is. Okay, let me continue with example 2. Now let's go for example 2, market clearing problem with linear offers. So this is really the market problem, because let's say the CG is not necessarily the cost of generators, but their offer prices, right? And it's a very simple setup. Again, 3 generators, no single inelastic demand, no transmission network. So we already talked that since the original objective function is linear, we need to use augmented version of Lagrangian relaxation. So equivalently, we can write this problem as it is. So we have max min problem. Lambda is the dual variable of the complicating constraint, which is the balance equality, and the added quadratic penalty term. And you know the whole story. So we fixed lambda to lambda bar, max is gone, but now this problem is not decomposable. But what we can do, we can use Adm, right? So not decompose, we talked why last time. So what we can do, we can use Adm setup. So now we have one subproblem per generator. So PG is the local variable of generator G. That's the, let's say, production cost. If CG is really marginal cost, then this is the revenue, and we have a penalty, right? So the objective function is not profit. Just the first 2 term refers to the profit. So it's a profit plus a penalty. Let's look at this penalty. So to be able to solve this problem, the generator G needs to know the demand and the production of other generators. Mathematically, it's correct, right? Mathematically, the generator G1, let's say, to be able to solve this ADMM problem, its own subproblem in the ADMM process, needs to know the demand and the production of the others in the previous iteration. And this is the way we can update price, but let's have a schematic illustrative presentation of this problem. Now, again, we have 3 generators. Each of them, they are solving their own problem, maximizing profit while, let's say minimizing minus profit plus the penalty term. And for example, for generator 1, sorry. So these are the, it's our local variable done. But now we need the generator 1 needs to know demand and also the production of rivals in the previous iteration. Is it clear? Yes. So this is tricky. At least, we will talk about that, but let's talk mathematically so far. So now again, we have auctioneer or coordinator or whatever you like to call, and the coordinator's job is to update price. So this time, the 3 generators, they respond to what? To not only the price, but also the production of others. Definitely there is no privacy. But mathematically, it's distributed algorithm, right? So computationally, it's nice, but definitely there is no privacy preservation. Is it clear? Good. So this is one of the challenges if we use a Valrassian auction for market clearing if objective functions are linear. That's a challenge. That's a challenge. Because we need more information to be exchanged between auctioneer and each market participants. Drake, a very good question. That's exactly one of my next slides. Drake asked, couldn't the coordinator just send D minus the production, the total production of others? Yeah, very good. But it's still, Drake, you're right, but it's still it's additional information compared to Lagrangian relaxation. So in each iteration, each generator needs to know more information. So is it really a Valrassian action? I don't know. Maybe you can call it yes or say yes or no. But what is clear is that we need more information to be exchanged. So this is a nice, how to say, way to warm up our next discussion, which is about exchange ADMM and consensus ADMM. So with exchange ADMM, we will try to somehow, as Drake suggested, overcome this challenge. The information we need, the amount of information we need to exchange between coordinator and each subproblem. Okay, we have to talk about exchange ADMM, but we talked for 48 minutes. Maybe it's good to go for a break of 12 minutes. And we can start again at sharply at 5. So let's go, let's have a 12-minute and now 11 minutes break. So see you in 11 minutes. Okay, let's continue. So now we are going to talk about exchange ADMM. Sorry. Yep. So let's get back to our original problem or its generalization. Let's assume that, again, it's a market clearing problem with I participants. So each market participant has a separate objective function, f of xi, fi of xi, and the local constraints and power balance equality. So, here again, we assume that our demand is inelastic, but just if it's elastic, it will be xi minus t is equal to 0 for all generators. So not a big change. So again, we can use ADMM to solve the problem for each I. So what we did, we fixed lambda, we bring the power balance equality to the objective function, we add the penalty term, and then we keep the local constraints in the constraints. And then the problem of each subproblem for each generator for each I will be the local objective function from the, it's the production cost, then the lambda bar, and yes, the penalty term. Yes, so here the xi in iteration no, it's a variable, while the production of all others and demand, they are parameters for a given market participant I. And this is how we can update lambda bar. So let's see what we can do, but already Drake mentioned in the chat box. So let's say that the total production of all generators, let's say it's equal to n times x bar, and x bar is the average production of all generators in iteration new, right? It's okay. So what we can do, so then this term in the penalty term, it's the total production of, it's the average production times the number of participants minus our current, the generation of underlying participant I in the previous iteration. So what happens, as Drake said, in Exchange ADMM is nothing different substationally. It's the same as ADMM we had. Just the only thing is that the extra information we need to exchange among the subproblems and auctioneer compared to Lagrangian relaxation is the average production and the demand. But that's the all extra information we need to share between auctioneer and subproblem. So you don't need to share all information of each specific rival. So an example with 3 generators, right? So each generator, they submit their response, their quantity to be produced, and what receives is the price, and let's say P bar, which is the average production of all generators. So then each market participants, yeah, here 3 is the number of generators, 3. So it's a common information for everyone. P bar is a common information for everyone. And also D here is a common information for everyone. So we have extra information to be changed, to be exchanged in the ADMM approach compared to Lagrangian relaxation. But that's the best we can do. Good. How we can generalize it by adding elastic demand or transmission network, exactly the same story we had for Lagrangian relaxation. We need to add the force subproblem for demand if it's elastic to price. Also, we need to add additional subproblem for transmission system operator. Okay. But remember, if we add transmission system operator, then instead of lambda bar, we will have lambda bar n. We will have nodal prices. Also, the power balance equality to be relaxed. It's, let's say, the total generations in node n minus the total demand in node n minus, let's say, all the flows from n to m, and m connects to bus n is equal to 0. So this says the constraint to be relaxed. So since we also have f and m here, and we are penalizing, I mean, we will penalize all objective function based on that. So now also the subproblem of transmission system operator will get a penalty term as a function of f and m. So now with exchange ADMM, the subproblem of transmission system owner is also quadratic because we will add a penalty term for that. Is it clear? Yes. So since that we solved the issue, so the transmission system owner has quadratic objective function here. But again, my students in the last versions of the course, they also tried exchange ADMM for the market clearing problem, and still they couldn't get convergence. And still it's open question to me why it didn't happen. So if you are interested, and if you choose this specific type of decomposition for your problem, if you would like to decompose your problem by agent and you go for exchange ADMM, so maybe you can try it, but don't surprise if you don't get convergence. But we don't know why. Actually, at the moment, I don't know why it doesn't happen. Is it a mathematical issue or is it a numerical issue? If you manage to get convergence, if you find a trick, that would be amazing, and you will get a very good grade in this course. Deal? Do we have a deal? Deal. Very good. Nice. But now I like to talk about consensus ADMM, which is very helpful, very efficient technique. And you will see that it has a lot of applications in power and energy systems. But before talking about consensus ADMM, do you have any questions so far? No. Is everything clear? I like to see at least 10 clear in the chat box. Yes. Good, good, good. Thank you. Uh, so Prawat says, I'm sorry to bring this up. Intended to do so during the previous break. Totally random, but since class might be rather. Okay, okay. There's a comment by Prabhat that everyone can read. It's not a question. Good. This is the last lecture, but not the last session. Remember, Monday, we will have 2 Q&A sessions from 3 to 4, and then from 5 to 6 p.m. CET, the European time. Okay, let's talk about consensus ADMM. Let's talk about fundamentals first. Check this problem. What does it say? It's a very specific problem. Can you explain what it's saying? Why we call it consensus? Maybe one of you can unmute and say. Jan says, because agents have to agree on X. Yep.
Yes, so this problem is actually decomposed somewhat in for the cost function. So we have fi, and the constraints are also for the separate agents, but all agents share the variable x. So they need to agree on this variable x and need to find a consensus for that.
Very good, very good, very good. So we have I number of agents. Let's say I number of agents. So we have multiple agents. Each of them, they have their own objective function, but the only variable to be determined, I mean, it's a common variable. It's a consensus variable, if you like, and it's x. X doesn't have index I. So all agents, yeah, they have their own objective function, but all as a function of common variable, right? Well, this is a very stylized problem. Also, you can assume that each generator or each I, they also have their own variables from also, for example, yi, and then you can add something related to one yi. It's fine. So it will not limit the applications of consensus ADMM. In consensus ADMM, the important thing is that there is a variable which is common among all participants or among all agents or subproblems, and we need to get a consensus to reach a consensus on the optimal value of x. Is it clear? So this problem is global consensus problem, since all agents should agree on x. Very good. So let's see how we can solve it through ADMM, not directly, but by decomposition techniques. First, we need to have a complicating constraint. So what we do is that we add, so what we do, we relax x to be xi dependent. And then we add a constraint, something like non-anticipativity conditions that you saw for two-stage stochastic programs. So for all i's, I mean, the variable at the end, we should get a consensus. So z is also a variable. Z is a dummy variable, auxiliary variable. So now we added a new constraint. It's something similar to non-anticipativity condition. So z is a new auxiliary variable, and all x they took index I. And clearly, the last constraint is our complicating constraint, right? Good. So we can relax the last constraint, and then we can use ADMM. So it's easy. We can remove it. Then we can add it here. It's lambda I Do you agree that we need index I here? Right? Because it's 1 per I. Yes? So lambda I for all I xi minus c. Right? Then also we can add the penalty term, which is for all I xi minus z square, right? And at the beginning, max is a dual variable that we are gonna fix it. So if we do it, and like always, we use Admm process. So this will be our X update problem, X1 per agent. Each agent, they are solving their own Xi. So now as you see, though X originally was a common variable, now iteratively, at each iteration, each participant makes her own decision about Xi. So in each iteration, the values of xi for different participants for different I might be different, but over iterations, they should get agreed on the value of xi. So for example, in iteration 1, if we have 2 agents, I1 and I2, their optimal value for xi could be, I don't know, 10 and 5. It's not okay. Then we go for iteration 2. Then both of them, they are compromising. Maybe this go to 9, this go to 6. And we continue this iterations till both of them, they reach, for example, xi equal to 7. And here we converge to a common agreement on variable xi, which is now is equal to x. Is it clear? Yes? Good. So we have X update problem. So this comes from the original objective function. It's objective function of agent I. This is the dual variable of fixing constraint. And remember, it's I indexed. This is the, again, our variable. Again, our variable and z. It's the auxiliary, the dummy variable we created, and subject to our local constraint. So it's kind of the same as what we had. Then we have our z update problem. Remember, z was auxiliary variable. We don't have any constraint for z update problem. So what it is, z didn't appear in the original objective function. So we have nothing as a local objective function for z update problem. So what we have is similar to this. Remember, our constraint to be, relaxed was xi is equal to z for all I. So here, if we write it in a canonical form, say xi minus z is equal to 0. So this is why we have minus. Minus comes from here, the same dual variable. And this time our local variable is z, because x is given in the z update problem. And our penalty term. And here we assume that we solve the two subproblems sequentially in each iteration. It's up to you. Also, you can write it xi in the previous iteration. We already talked about that. Is it clear? This xi update and z update subproblems. No question? I hope it's clear. So then we have y bar update that we already see how it works. Good. So this is how we can solve our consensus problem using Adm. It looks fine, but we can further simplify this problem. Let's see how. Let's focus on z update problem. Let's focus on z update. And the first thing is that it's unconstrained problem, right? We don't need to really optimize it by, I don't know, a solver. We can easily find the optimal value of Z. Maybe you can help me to derive the optimal value for Z. It's just the objective function. If you write a Lagrangian function, nothing comes from the constraint because there is no constraint. So just we need to take the derivative, the partial derivative of objective function with respect to Z and make it equal to 0. So if we say the derivative of Lagrangian function with respect to Z in iteration nu will be simply equal to, maybe you can help me. So from the first term, it looks like this, minus, let's say, lambda 1z plus lambda 2z plus blah, blah, blah. So if we take derivatives of z, it would be just minus of all summation of all lambda bars. So it's minus I from 1 to n, lambda I bar in the previous iteration. Now let's take derivative of Lagrangian function, this term with respect to z. So it should be plus gamma half, then this 2, the derivative of inside, which is minus 1, right? And then the term inside, xi nu minus z nu is equal to 0. Do you agree? And I forgot the sum operator. Good. So if we do this, then we will have what? We will have simply I1 and lambda bar in the previous iterations plus, not plus anymore, it's minus I from 1 to n. Let's have gamma here, xi in the previous iteration, plus gamma from I to n z in the previous iteration is equal to 0. Right? Hope I'm correct. So here we can simply write it gamma. I mean, z is not a function of I. So we are repeating z n time. So it's just gamma and z. Right? So what we end up, if I'm not wrong, is we would like to write the value of z. So gamma and z, if we put it the other way around, then it will be gamma I from 1 to n, xi in the previous iteration, nu minus the other one, I from 1 to n, lambda bar in the previous iteration, I. Right? And then the value of z, it will be the same over gamma n. That's it. So I made a mistake somewhere. It should be positive. Yeah, I made its derivative formulation. Yes, anyway. So if you check it out, finally, we will end up to this formulation. Okay. So now z, we know the optimal value of z as a function of given x and given lambda bar. That's it. So we don't need to solve the update problem anymore. It's just equation. And we can call this the update problem as a central collector or fusion sender, if you like. So now in our consensus ADMM problem, the update is an equality. It's not an optimization problem anymore. Good. Nice. Yeah, yes. Is it clear so far? Good. So let's see what we can do. Is there any way to further simplify the consensus ADMM problem or not? We simplified this. Let's see if we simplify, can we simplify the others or not? So what we can do here, we can say that the z in the iteration nu, this first term is simply the average of x over all I number of agents. So we can call it x bar in iteration nu. It's the average value of common variable among all agents. And the same goes for the other one. So we have 1 over omega, the average value of lambda for all agents in the previous iteration. It's okay, right? It's just a definition. We can do the same for the last one. We can say we can take average from the both sides. We can say that the average value of lambda bar in the current iteration is equal to the average value of lambda bar in the previous iteration plus gamma and their average. So the average of x among all agents, it's x bar, and z is common, and its average is again, it's z. Sebastian says, if all we had was a complicating variable, why didn't we just use benders? Am I missing something? Well, you can also use benders, but also we like to solve it by ADMM, and you will see that we will finally end up in a very easy setup. I agree, z from the beginning, it looks like complicating variable, but now we like to solve it by as a complicating constraint, just a different alternative. Is it clear so far? These two equalities, are they okay? Good. Let's see if we put together what will happen. Easily, please put the value of z here. Maybe you can check for a minute and see what we will understand, what we will get. So here we will have lambda bar in a previous iteration is lambda bar in the previous iteration, lambda bar in current iteration minus lambda equal to lambda bar in previous iteration plus gamma x bar in the current iteration minus not this term x bar in the previous iteration minus 1 over gamma lambda bar in the previous iteration. All right. So what happens? This term and this term, they cancel out each other. And these two, yeah, I'm doing the correct thing, right? And then this term and this term, they will cancel out each other. And at the end of the day, lambda bar in iteration nu is equal to 0. Exactly. So what happens? Lambda bar in current iteration is equal to 0. And if it's equal to 0, this is equal to 0. And just z in iteration nu is equal to x bar iteration nu. So what does it mean? It means that we don't need to have z anymore. We can replace z with x bar. Let's see here. Remember, average lambda is equal to 0, not lambda I. So still we need to update the value of lambda I, not average lambda. But instead of z this time, I'm replacing x bar, the average value of x. So we created dummy variable, auxiliary variable z, and now here we got rid of z. Now we found the optimal value of z as a function of average x. So now mathematically, we will end it up to this problem. There is no z update anymore. Just we need to update lambda for each I, and this is our objective function. So Raja says, beautiful. Raja, can you interpret now this final form? What we are doing? What does it say? What does this say? We are penalizing based on what? Every agent, they find the optimal value of xi, the value of common variable from their own perspective, and then over iterations, they penalize their current value with respect to average value of the common variable among all agents. Right? So for example, if the first iteration you get 10 and 15, then the average is 12.5. So in the next iteration, the people, they penalize their objective function saying that x minus 12.5. And also here, x minus 12.5. So they are penalizing their objective function over iterations with respect to average value of the common variable among all agents. And this way they are reaching a consensus, right? They are reaching a consensus. Is it clear? So what happens? So we got rid of z. This formulation simply means that in each iteration new, each agent I independently solves its own subproblem to determine the value of global variable or common variable xi, while penalized based on its distance to the average value of global variable, common variable, among all agents obtained in the previous iteration. Hope it's clear. And this technique is also called in the literature as progressive hedging. I don't know if you have heard of this method or not. The basics of progressive hedging is exactly the same as consensus ADM. Any questions so far? Is everything clear? Yes. Nice. We have a few discussion here. First is scenario decomposition. Sebastian says, what are the conditions for convergence? Again, the same conditions as convergence for ADMM that we talked yesterday. The problem should be convex, the original problem. Slater conditions should hold. There should be a solution. And we should have continuity, Lipschitz continuity. Lee talks about should we have synchronization of solving these two problems? Here, yeah, the problems we can solve in parallel, right? There is no sequentiality. In each iteration, I number of agents, they are solving their own problems separately and in parallel, and then we go next iteration. So each iteration, every subproblem in parallel. If we have, 100 agents, we solve 100 problems at each iteration in parallel. Raja says, can you give some application examples of consensus? Yeah, this is exactly what I'm gonna do, Raja. Yeah, I have 2 examples right now. Good. Scenario decomposition. Is this problem familiar to you? It is, right? It's our 2-stage stochastic market clearing problem. Exactly. You had a few alternatives. One is treating PG day ahead as complicating variables and to solve it by benders. We already talked about that. But now let's see what our other alternatives is. You will see that it's way simpler than benders. Can we solve it as a consensus Adm problem? If so, what is the common variable? And what are the agents here? Not the agents, what are the subproblems? What is the common variable to reach consensus on it? And who are they getting consensus on it? Sebastian says PG day ahead, exactly. PG day ahead is the common variable, or if you like to call it, you can call it coolable variable or whatever you like. Yes, it's our common variable. Common variable among who? Common variable for scenarios. Common variable for scenarios. So all scenarios, they should get agreed on the value of PG day ahead. So we will have scenario decomposition. So maybe you can help me. This is our two-stage problem. And this is the formulation we got for consensus Adm. So can you help me to drive scenario decomposition formulation of two-stage problem using consensus Adm? So let's do together. Is there any volunteer who would like to unmute and help me? We like to write this problem. We like to write this problem in the form of consensus Adm. Any volunteer to help me? We will write together. It should be easy, no worries.
All right, sure. I'll
Good,
try.
Sebastian. Good.
So
Sebastian, so we agreed that we are gonna consider PG day ahead as a common variable, right?
Mm-hmm.
So we are gonna relax it to PG omega day ahead for all generators, right?
Yeah.
Good, thank you. So now I'm trying to write this problem for our stochastic market clearing problem. So I'm writing minimization, right? Let's see what the variable. So what are the variables?
I mean, each subproblem has its own real-time generated dispatch and its shed power.
And the common variable.
And the common variable, of course. I mean, the other constraints I think are less important.
Yes, very good. So PG omega day ahead. So now we put omega for the first stage variable everywhere.
Mm-hmm.
So this one, then the other two, PG omega real time and PD omega shed. This is our three variables in each subproblem. And you agree that each subproblem will be 1 per omega, right?
Yeah.
Very good. What about the objective function of the subproblem?
Objective function of the subproblem is going to look very similar to the main objective function.
Yes, okay. Cos day ahead as a function of PG omega day ahead. Good.
Also minimizing the cost of the real time.
Exactly. But for, should I put expected operator or not?
I think not.
Thank you. So let's say phi omega, the corresponding probability. Cost of real time as a function of PG omega real time and PD omega load shedding. Okay, I will have a large, objective function, a long objective function. Good. So now you wrote this part. Now we need to write this part, right? Sebastian? Okay. So now we like to write this part. So what should it be? Plus, for this part.
Yeah, so lambda is going to be for the complicating variable. So I'm going to guess it's on the first.
So what is
Lambda
the,
times PG
yes,
omega?
exactly. So this is our
Yeah.
constraint that we relaxed.
Yeah.
The lambda should be lambda, G, and omega, right?
Lambda G and omega, yeah.
Very
And
good.
then
Lambda G omega. Let me say bar. Okay, I need to put what to say? The iterations everywhere.
yeah, the iterations, because I think we now need PG omega day ahead from the previous iteration.
Yes, exactly. Okay, so X. So not the star. It's the current variable, right? So it's PG omega day ahead in current iteration.
Mm-hmm.
So we finished this part. Not yet. So our objective function, I mean, now, okay, we have 1 per omega, but also we have index G. What should we do? We also did
So we need the sum over the
sum.
G's.
Exactly. So let me write it a bit here, plus sum over G. Very good. So we finished this part. Now this part, the last part.
Yeah, that
Okay.
part should just be gamma over 2, and then the
Okay, gamma over 2.
xi stays the same, so that's PG omega dA of a
In the
current
current-
iteration minus the average of the previous iteration.
Very good. So I would say PG. Do I need to write omega? It's average.
No, it's average, so we don't count.
Very good. Average in the previous iteration. Good. The score. Do I need something?
The average PG is for each PG again. So this is sum over G again.
Exactly. Done. Okay, finished.
A question for the notation, the double vertical lines, is that absolute or?
No, it's
Oh.
a norm function.
So let's see.
It's a norm function. You can say it's just a score.
Okay. Right.
Okay, it's just a score. This term score. Okay, what is the constraint?
The constraints are just G and H.
And F.
Okay.
Also this, right? We are not fixing it. We are just relaxing. We need to include it still. Am I right?
I guess.
Okay, so we have 3 constraints. F of PG omega day ahead is lower than or equal to 0. G of, yeah, exactly the same. PG omega real time and PD omega shed is lower than or equal to 0. And I'm writing the last constraint here, H of PG day ahead omega, PG omega real time, and PD omega shed is lower than or equal to 0. All of them for subproblem omega, and I need iteration new for all of them. Okay, done. That's our subproblem. 1 per scenario. Done. Now we need to write a Y update problem. I'm gonna write it in a different color. Let's say I don't know. Yeah, blue or purple. So Sebastian, are you there also to help me to write the last one, the lambda update subproblem, not subproblem, lambda update problem. So
Sure.
here lambda bar. So lambda bar came here, G omega in iteration new comes from the previous one, G
Comes from the
omega.
previous lambda bar.
Yes.
Gamma times, and then that term looks like the inside of our penalty term, I think.
Yes. So it's PG.
PG omega day ahead current iteration minus the average of the previous iteration.
Very good. I don't call it previous iteration because after solving all the subproblems, Now we know what the updated value
Yeah, sorry,
average
it's
is,
not
right?
it's not previous.
So,
Yeah.
so not the previous, the current one.
Do we need a sum over G somewhere?
No, because it's
Also, because
one
we're
lambda.
calculating for each G. Yeah.
So it's 1 per G, 1 per omega. Done. So simply you solve each subproblem per scenario. And then you'll find the updated value, the value for PG they had in that scenario. Then over the iterations, you penalize the objective function to, you penalize based on the average value. That's it. There is no master problem compared to Bender's decomposition, just subproblem. If you would like to say the master problem is just lambda bar update, which is way simpler than Bender's master problem. Isn't that beautiful? Wow, very good. So Rafa says very good. Any question? So you see the scenario decomposition. Yeah, you can do it by Bender's. I'm not against that. I love it. But with consensus ADMM, it's way easier. Good. Yes. Raja asked the applications. So let's go for the next application. If there is no question here, I can go for next application. Liang said, I think phi should be applied to both data and real-time cost for each subproblem. We have it here, right?
Yeah, but I think it should also be applied to the cost of day ahead term, because then you have to, yeah, exactly. Because you have to, all the subproblems have to add up to the original problem, right? And for each subproblem,
Not here, not here. I don't think so. Just you relax it.
yeah, but because if you think of decomposing a problem, you have to have all the subproblems add up to the original problem. And now you basically, if you add all the subproblems
Yeah, I see.
Together.
Yeah, in that sense, you're right, Liang. Yeah, all subproblems together should end up to that one. So Liang says we also need phi omega here. It might be correct, but I'm not sure. So I'll leave it as an open point. So we have to check it later if we need it or not. But thank you, Liang.
Yeah, I'm not sure either.
I'm not also sure either here right away. Yes. Any other question? Is everything clear? Can I go next example? Yes. Okay, nodal decomposition. Have you heard of that? Okay, let me say, I will not write equations. Lee says, I think so. We may also change the coefficients to be 1 over n, or another can sum up as 1. Lee, which part you're saying?
I'm just, talking to what Leon suggested to add the probability also to the term related to the day ahead cost.
Mm-hmm.
So if we have to, to be the decomposed sum problem have to be add up with the same as the original problem from the objective function. So maybe we also can, break up the original cost dA to, equally separated by, using the the probability could be n over 1, right?
The probability of 4 scenarios?
Yeah, because here Leon just suggested to add the probability of each scenario.
Ah,
and
so your
then
question is
we
that
will add up with this, yeah.
So your question is that should it be phi omega or should it be 1 over the number of scenarios? This is your question, right?
Yeah, yes. I mean, like, I'm not sure, but if we're thinking that way, like the sum of the objective of decompose subproblem should be added up with the same as the original problem, then we can even change the coefficient for each term. We can change any other kind of coefficient whose sum up can be 1, right? I mean,
Actually, now I'm thinking that even we don't need none of them. That's my first
yeah.
impression. Because
Yeah.
here, not, I mean, like it's not benders that we are reconstructing the objective function.
Mhm.
Just we are relaxing
Yeah.
PG omega to be agent dependent or here scenario dependent. And then
Yeah.
over the scenarios, they have to get agreed on all of them. So even I don't think that we need either phi omega or 1 over the number of scenarios. I think we should leave it as it is. That's my first.
Yeah. Okay.
Oh, actually, I think if you, because you have to think about if you each subproblem has to make sense for all the sub scenarios, and if you don't add that coefficient, then if you look at the subproblem itself, it doesn't really make sense for a scenario, because for the scenario itself, you have to have a day ahead stage and a real-time stage.
Yeah, okay, I agree. But for PG day ahead, for someone is 10 megawatt, for other one is 12, for other one is 15, but we don't need to wait day at the stage by 5.
Yeah, but then, okay, we can discuss this later, but I think we do need that coefficient.
Okay, we have a disagreement here with Leon. Yannick, what do you think?
Well, I think if you calculate the objective function value of the original problem using the original objective function, then it shouldn't be a difference because you have like the variables, right? But the sum of the subproblem's objective function values shouldn't equal the overall objective function value when you don't add this coefficient.
So you agree with me?
I think it doesn't matter for the variables, like for the optimal variables. But for the objective function value, it matters
Okay.
if you put it on. But yeah, we can talk later.
Anyway, I'll leave it as open question. It should not be, yeah. It should not be very critical problem. Good. Let me talk about nodal decomposition. What nodal decomposition is, consider the following 3-node network. And this figure comes from Vladimir's PhD thesis. So thanks him for this nice plot. So how to decompose this problem? So we would like to solve the OPF problem, optimal power flow problem, let's say for this 3-node system. How to decompose this system by node and solve the resulting distributed OPF problem, 1 OPF problem per node using consensus Adm. So instead of solving 1 OPF problem for the whole system, we would like to solve OPF problem in a distributed manner, 1 OPF for node 2, 1 OPF for node 1, and 1 OPF problem for node 3, and solve them separately but iteratively. Is the question clear? Any idea how can we do that? And that would be amazing. Assume that you have a system of, I don't know, thousands of nodes. If we manage to decompose it by node, that would be amazing. So any idea how we can decompose it? And the question is, we would like to solve, use consensus Adm. So what the common variable is here? So the answer is, we can consider this network as this decomposed network. Just we need to generate some auxiliary variables. So maybe I can give you a minute that you can think what we did here, and one of you can explain, can unmute and explain what we are doing here. Copy the variables. Yes, exactly, Lee. So what is the consensus variable? What are the local variables? Let me write, for example, for node 2. For node 2. In the original problem, the flu, if we write a power balance equality for node 2, it's just P generation at node 2 minus the demand at node 2 minus the flow from bus, the flow from node 2 to 1. So B theta 2 minus theta 1 is equal to 0. It's our power balance equality in node 2. Now, if we like to decompose our problem, original OPF problem, to 3 subproblems, 1 per node, let me write the subproblem for node 2 only. The same way you can write for nodes 1 and 3. So here the objective function is the cost. I would say just the cost related to generation located at that bus. So whatever it is, subject to assuming that the demand is inelastic. So also we have, I don't know, the limitations for PG2. So f of PG2 is lower than or equal to 0. Some functions related to the generation at node 2. But what is the power flow, in node N2? Here we have this one. So it should be, I'm writing the power flow or let me write the power balance equality at bus 2. So like this, so PG2 minus PD2. Remember in the original form, theta 2 is a local variable for node 2, but not theta 1. Theta 1 is a variable for other node. But what we can do here, we can write minus B. Instead of theta 2, I can write theta 2, which is equal to theta 2 at the end of the day, it should be, minus, instead of theta 1, which is here, I write a copy of it, but from node 2's perspective. So it's theta 1, 2 is equal to 0. Right? So this is theta 1, but from node 2's perspective. Now both theta 2, 2 and theta 1, 2, they are variables for node 2 and also the local generation. Also, we need to add the transmission limit constraint. Is it clear? So now I managed to write a distributed nodal OPF problem, let's say just for node 2. We can do the same for node 1 and 3. So now what are the variables, the common variables between the nodes? They are this. So in this case, theta 1, 2 is here. So for this variable, the node 2 should get agreed with node 3 and node 1. So it's a common variable between 3 nodes. While theta 2, 2 is a common variable between node 1 and node 2. So here we have 3 variables or consensus variable, common variables to get agreed between different nodes. And of course, you need to add the penalty terms that we had in the consensus Adm. Is it clear? Hosna says yes. What about others? Is it clear what we are doing? So we call it nodal decomposition, and also it uses the concept of consensus Adm. Good. So Raja, I hope I provided you with enough applications in power systems, but I will provide a conclusion later. Okay. Now I have the last discussion of the lecture. Let's say in each iteration we need to solve 1 million subproblems. To go to the next iteration, do we need to have all subproblems solved or not? In our scenario decomposition problem, let's say we have 1,000 scenarios. In each iteration, should we solve each subproblem related to each scenario and then to go to the next iteration? Is it necessary? Direct says it might converge faster, but no. In the way I explained ADM, yes, we need to solve all subproblems in each iteration, and then we can go to the next iteration. But what happens if one subproblem, for any reason, maybe the corresponding, I don't know, core is not working, or any computational issues in HPCs or whatever. Assume for any reason, if one subproblem takes way longer time to be solved than others. So 999 subproblems, they are solved, they are ready, but all of them, they are waiting for one lazy subproblem to be solved. Then this affects the whole ADM process, right? It compromises the computational time. So for that, in the literature, there is a synchronous ADM technique, and it explains how to not solve this, let's say, the time-consuming subproblem. We can leave it to be solved in iteration, let's say 2, and we go for iteration 3 for the rest of the subproblems, and wait for the lazy subproblem to find the solution and join to the process in iteration 5, for example. So I'm not going to teach what to do, but at least these two very nice references about asynchronous ADM, they explain how we can do that. And even we can further or robustify our distributed algorithm and make sure that we can solve all of them in parallel, and the computational time will be comparatively low. So is it clear, the concept of asynchronous ADM and what the goal is? Clear? Good. So this was my last discussion for the lecture and for the course. Just an overview of potential applications of decomposition, either Bender's or Lagrangian relaxation or ADM or any other Lagrangian, or any other decomposition techniques. So we saw that, and also it's for your project step 4. You can either decide to decompose your problem by agent, like Valrassian auction, and we can do it by exchange ADM. And remember, if you manage to solve it, if you have a transmission system operator, your grade will be amazing. That's our deal. Your second option is to decompose your problem by scenario. And you can do it either by Bender's or consensus ADM, at least. Then you can think of nodal or even zonal decomposition. You don't need to necessarily decompose by node. Also, you can say, okay, I decompose by a set of nodes, like a zone or area. The day-ahead market clearing in Europe, it's based on zonal market clearing, and usually each zone refers to a country. So you can even decompose your model by zone. How can we do that? It's by consensus ADM. You can also decompose by sector. For example, assume you have a DSO-TSO problem, distribution system operator and transmission system operator. So here it's a transmission area with the meshed network. And this is the low voltage distribution system with radial network. And at PCC, power coupling of, I forgot, in the interface, anyway, you have a network or whatever, right? And you have a constraint there. It's exactly like nodal decomposition. So you can relax the constraint here, and then you can have two subproblems, one for transmission system operator and one for DSO. Or if you have one TSO connected to, I don't know, 2 or 3 DSO, so you can decompose your problem, then you will have one TSO subproblem and 2 DSO subproblems. So you can go for DSO-TSO coordination problem using decomposition techniques. Also, in the same way, you can think of sector decomposition for integrated energy systems or for integrated networks in total. Now we are all thinking about integrated energy systems, power, heat, gas, water, transportation, whatever. So yeah, just because of transportation and water, I called it integrated infrastructures rather than integrated energy systems. Again, let's say that, I don't know, you have a coupling points between power system and heat system. It could be, I don't know, heat pumps, it could be CHPs or whatever. Again, you have to see what kind of linking you have. Is it a constraint or is it a variable? And then you can decompose your integrated energy system or integrated infrastructure system or problem, one per sector, one subproblem per sector. So how can you do that? Usually you have complicating constraint in that case, so you can use different variants of Lagrangian relaxation and Adm. So remember, for benders also, we decomposed our problem. If our problem was capacity expansion planning investment model, always the investment variable is a very great candidate to be considered as complicating variable. Then benders would be our alternative. Finally, mathematically, but it's a heuristic, if you have a mixed integer nonlinear program, maybe you could manage by fixing binary variables, you manage to recast it as a mixed integer linear program in the master problem, and nonlinear problems, but continuous nonlinear problems as subproblems. Though we know that the min-LP, that we don't have off-the-shelf solvers for that, maybe by benders, we can manage to solve it. Not necessarily to optimality, but efficient solution technique. How? By benders. And etc. Maybe there are also the other applications for decomposition techniques in power and energy systems. Yeah, that I forgot, but definitely you can easily, extend this list. And if you think of, there are many, many, many applications for decomposition in power and energy systems. Any question? Hosna said, how about decomposition by time slots? Yeah, you're right. I forgot it. Yes, you can also decompose by time, temporal decomposition. So it will be just by relaxing intertemporal constraints. Definitely. So definitely. So instead of etc. or here, we can also write decomposition by time. Composition by time. And again, you can use Lagrangian relaxation techniques. Good point, Hosna. Yes, relevant references, a few, all about distributed OPF. Yeah, you can find many numerous papers using different decomposition techniques for different applications in power systems. But for example, this paper from Yizhang and the group of Professor Giannakis, they are using ADMM for decomposing a stochastic market clearing problem, as far as I remember, not by scenario, but by area. There's a very nice paper by Ahmadi Khati Konacho and Cherkhoy they are using ADMM. Actually, it's not ADMM, it's augmented Lagrangian relaxation using APP, if I remember correctly, and they decompose the multi-area unit commitment problem by area. So one subproblem per area. So I already introduced this paper to you. It's decomposition per agent, if I remember correctly. I added this reference because it's application of decomposition to non-convex ACOPF. Yesterday we talked that under some circumstances, under some assumptions, we can guarantee the convergence, not to necessarily the coulombic point, but convergence to a stationary point. So it's a nice application. Also, this is a very nice paper by Peng and Professor Stephen Lowe. They first relax or convexify radial OPF in the radial systems by conic relaxation. Maybe you know that conic relaxation in radial systems under some mild assumptions, it's exact. Then they used nodal decomposition. So they have one subproblem per node in the radial systems, and they used consensus ADM. Yep. And then there are two nice survey papers in the literature. Both of them, they are a survey of distributed optimization techniques for power systems. And both of them, they are very nice techniques. Just one thing, sometimes you see that the people, they call it, they differentiate distributed and decentralized. All the techniques I taught, they are distributed because in all of them, you need to have a coordinator to update the dual variable, or in the benders, we need a master problem. But there are techniques with some tricks, decentralized. It means that the subproblems, they directly contact each other, and we don't need to have the main coordinator. And then we can call it decentralized composition. I didn't cover it in the course. Nuran said, can ADMM be used in multi-stage stochastic program? It should be. I've never thought of it, Nuran, to be honest. So you are thinking of counterpart of nested benders, but with ADMM. I've never thought of that. It might be possible. So I didn't think of it. It might be possible. And that's it. That's the yeah, that's the last the end of the last lecture. Thank you so much for attending this course. And yeah, hope you enjoyed the course, and hope you learned something out of the course, and you will be able to implement it in your current or future research. Thank you so much. We will have a meeting, Q&A meeting on Monday, but there will be no presentation anymore. Thank you, and see you on Monday if you attend Q&A session. Ciao.